We'll continue our discussion of Laplace transforms with the second shifting theorem. And the second shifting theorem is going to help us find Laplace transforms of piecewise defined power functions and power functions that have a shift in them themselves instead of the Laplace transform having a shift. So these functions are going to look like, I'm going to define our piecewise function as u sub a of t, and I'm going to include with it a shift of f of t minus a, and we'll take the Laplace of this. So our piecewise functions, we can always write them as unit step functions. And instead of having the Laplace with the s minus a shift, this f has a shift in it for the forcing function, itself. So it'll look like this. The Laplace of that is the integral from 0 to infinity e to the negative st times the function inside, u sub a of t times f of t minus a dt. Okay, so remember that u sub a is equal to 0 from 0 to a, and then 1 from a to infinity. So this is equivalent to the integral from a to infinity times of e to the negative st f of t minus a dt. Because that unit step function is 0 from 0 to a, and then it picks up at 1 from a to infinity. So we don't have to include the times 1. Now what I'm going to do here is a u sub. I'm going to let u be t minus a. So du is dt. And that means a couple of things. At t equals a, u would be 0. And our integral would turn into the integral from 0 to infinity e to the negative s times, t would be equal to u plus a, f of u du was equal to dt. Okay. Now remember, this is integrating with respect to u's. So as far as the integral is concerned, s and a behave like constants. So we can factor out e to the negative as in front of the integral. E to the negative as times the integral 0 to infinity, e to the negative su times f of u du. But this integral, it doesn't matter what variable we use. That integral right there is the Laplace transform of f, little f. So here is our second shifting theorem. It says the Laplace transform of a piecewise function, so unit step function of t, u sub a of t, times f of t minus a is equal to e to the negative as times the Laplace of f at t. So the e to the negative as takes care of two things. It takes care of the unit step function at a, and it takes care of the t minus a shift, and we can just multiply by the Laplace of the original function. So let me show you an example. Say we have to find the Laplace of f of t, where f of t is given by the piecewise defined function 0 and t minus 2 squared, where it's 0 from t goes 0 to 2, and t minus 2 squared at t is greater than or equal to 2. And I'm going to scroll up here so we can keep the theorem and the example on the same page. Okay, so we're going to find the Laplace of this. So the first thing to do is write the function in the unit step function format. So this is really the Laplace of u sub 2 of t times t minus 2 squared, because it's 0 until 2, and then at 2 we turn on t minus 2 squared. Now, one thing I want to point out, because we have a corollary coming up that's really crucial, it is very convenient that in our second shifting theorem, the t minus a matches the u sub a. So it's very convenient that t minus 2 here matches the 2 turning on and turning off. That is really an important point to make. And we'll deal with the fact that they might differ in the corollary. Okay, but for right now, we're going to apply this theorem. So the theorem says that the Laplace of u sub 2 of t times t minus 2 all squared is e to the negative as. Okay, so a is 2. So this will be e to the negative 2s times the Laplace of f of just t. So f of t would be t squared. The Laplace of t squared, we know that. That's 2 factorial over s cubed. So we have e to the negative 2s times 2 over s cubed. But again, I really want to acknowledge it was very convenient that this t had a shift of a 2, and so did this one. That's why we didn't have to find the Laplace of anything more complicated. Let's try one more just like that one before we move on to the harder ones. Okay, so we're going to find the Laplace for f of t is now given by the piecewise function 1 from 0 to 3, and e to the t minus 3 when t is greater than or equal to 3. Because I want to do a couple of things here. I want to practice this second shifting theorem one more time, and I want to show you what to do when you don't have 0 as your first function. So when we write this function f of t in unit step form, we start with 1 minus turn off 1 at time 3. So 1 minus turn off 1 at time 3. Then we add turn on e to the t minus 3 at time 3. So if you start with a function that's not 0, that's fine. Just put that in the front. Then turn it off when it says to turn it off, in this case at time 3, and turn on whatever functions you have. Now, the way we've written this function right here is really cumbersome for taking the Laplace transform, so I'm going to rewrite this by collecting my u3s. So I'm going to write 1 plus u3 times the quantity e to the t minus 3 minus 1. Okay. Then I'm going to take the Laplace of this. Okay, so the Laplace of 1, remember, is just 1 over s. The unit step function, whenever you see the unit step function, you always put in e to the negative as. So in this case, it will be e to the negative 3s. And then you check to see of your functions that have variables. So don't worry about the constant function 1 over here. But of your functions that have variables, the variables should have a shift, that matches your a. So if you have a u sub 3, the variables should have a shift of 3. And if they do, awesome. Then you're just finding the Laplace of e to the t, and you can ignore the t minus 3 part. So that was, because you already took care of it with the e to the negative 3s out front. That already took care of our shift. So this Laplace transform was 1 over s minus 1. So this will be 1 over s minus 1. And the Laplace transform of 1 is 1 over s. Okay. So the 1 out front has a 1 over s Laplace transform without an e because there was no unit step function there. But there's a unit step function applied to the e to the t minus 3 and the minus 1 inside the parentheses. So they should both be multiplied by e to the negative 3s. And that takes care of any shifts of t minus 3. Since the e has a shift of a t minus 3, I just find the Laplace transform of f of t. So the Laplace transform of f of t is 1 over s minus 1. And 1 already has all the shifts taken care of, so the Laplace transform of 1 is just 1 over s. Okay, let me pause this. I want to state the corollary and then practice a bunch where there might not be a shift that matches the unit step function. So it might look something like this. So before I write the corollary, I want to show you what this will look like. We're going to find the Laplace transform of, I'll do the writing the piecewise function for you in the unit step function way. So let's just write the f of t already as a unit step function. I want to write it as u sub, oh, I can't read my writing, u sub 1 of t times t squared. So if you want to see that, that would have been, just as an aside, 0 or t squared when t goes 0 to 1 or t is greater than or equal to 1. So notice that the t doesn't have the same shift as the a, which we need to make up for. So here's what our corollary says that we're going to do in order to compensate for that. It says the Laplace transform of the unit step function at a times just f of t is still equal to the e to the negative as, so that's still going to account for our unit step function and the shift. But think about what shift might have happened here. We still can call f of t minus a if it was f of t plus a minus a. So if this t right here were a t plus a, then the t in the answer would be a t plus a. Then the second shifting theorem holds. T plus a minus a is just f of t. And we can apply the theorem as normal. So this would be times the Laplace of f of t plus a. So in this case, for this example, the Laplace of u sub 1 times t squared is equal to e to the negative 1s times the Laplace of t plus 1 all squared. So the plus 1, because this t didn't have the appropriate shift, the function that would have had the appropriate shift would have been t plus 1 minus 1. So this would have been a shift. Kind of think of a u sub. So I have the Laplace of t plus 1 all squared. Oh, that's a bummer. I don't know the Laplace of t plus 1 quantity squared. I do know the Laplace, though, of t squared plus 2t plus 1. So I could always FOIL it out if I needed to. So this would be e to the negative s times the quantity. So the Laplace of t squared is 2 over s cubed the Laplace of 2 times t is 2 times 1 over s squared, and the Laplace of 1 is 1 over s. Okay, so if you don't have the correct shift in your function, that's fine, make it. So add, if it's a 1, add 1. Then you've added 1 and subtracted 1, and the subtracted 1 part counts from the shift. The subtracted 1 part cancels out from the shift, and the added 1 part needs to be taken into consideration. Okay, I'd like to try 2 more examples, some that have shifts and some that do not, so we can practice. And then we'll finish with 2 rigorous solving initial value problems in second order differential equations. So let's find the Laplace transform for f of t equals u at pi halves of t times cosine of t minus pi halves. Okay, so I already wrote the piecewise function in the unit step function for you. I'm being a little lazy. I'm not writing in the u of t, but u is a function of t. And then, let's see, to take the Laplace. So the unit step function starts at pi halves. So we'll have e to the negative pi halves s. And thank goodness cosine has the correct shift. So this will just be the Laplace transform of cosine of t. And that is s over s squared plus 1 squared. Okay, so since we have the appropriate shift already taken into consideration for cosine, this is e to the negative pi halves s times s over s squared plus 1. Okay, let's try one more. Let's find the Laplace transform for f of t equals u sub 7 of t times t cubed. Okay, so the Laplace of this f would be e to the negative 7s times the Laplace of t plus 7 all cubed. Ugh, okay, because that doesn't have the correct shift in there, unlike the last one. I don't have a good way of finding the Laplace of this, so for right now, I'm stuck doing t cubed plus 7t squared plus 49t plus 343. Lovely. Okay, so this is e to the negative 7s times the Laplace of t cubed is 3 factorial over s to the 4th. The Laplace of 7t squared is 7 times 2 factorial over s cubed. The Laplace of 49t is 49 times 1 factorial over s squared. And the Laplace of 343 is 343 over s. Lovely. One more thing to practice before we solve those 2 initial value problems. Let's take the inverse Laplace. So let's do that next. All right, first problem. Let's find the inverse Laplace of e to the negative 2s over s squared. Okay, so now remember from the problems we were just doing, these came from a unit step function at a. So since we have an e to the negative 2s, that was a unit step function at 2. And I'm going to make that 2 red, because that 2 is going to be really important, of t. Now remember, we can't see the shift in our Laplace transform for the s squared. So we have to show the shift over here. And we took care of it if the shift wasn't reflected. We just had a bunch of terms. So the s squared, let's see, write this in green. Somebody's Laplace transform 1 over s squared, g of s is 1 over s squared. That came from having just t, right? That the Laplace transform of t is s squared. So the reason I'm writing that and calling it g's instead of s's, instead of f, is I want this to be my function. I want t, but I have to show that it had a shift of 2 in it. Because remember, when we did the shifting theorem problems just a minute ago, we took the Laplace transform of just the original function and we didn't include the shift. We allowed the e to the negative 2s to include the shift. So now going backwards, we have to reflect that. So writing this only in one color, this is u sub 2 of t times t minus 2. I find writing this in green over here, the g of s is 1 over s squared, so it came from g of t equals t, to be really helpful. So let's do a couple more. Let's find the inverse Laplace of the function e to the negative s over s plus 1. Okay, so this will be the unit step function at 1, and let's see, this was g of s is 1 over s plus 1. That came from a function e to the negative t. So when we go back and write this, we want to put e to the negative t, but we have to show that there was a shift. So it's going to be t minus 1. So e to the negative quantity t minus 1 times u1. Okay, let's do a couple more. Scroll up. C. We'll find the inverse Laplace for e to the negative 7s over s squared plus 9. Okay, so this came from unit step function of at 7, and g of s 1 over s squared plus 9. Okay, that is a sine of 3t, although it needed a 3 in the top, so we need to compensate with a 1/3 out front. And I'm regretting writing that in red, because when I go back and write this, I want to write 1/3 sine of 3. Now I'm going to say this a little differently for the last two, just so you get more of a practical way of doing these. I want to put in sine of 3t, but I need to show the shift of 7. So it'll be sine of 3t minus 7. And I'm going to highlight in red minus 7 and 7. And I'll say that again. In order to show a shift of a 7, a unit step function with a 7, everywhere I put a t, I have to put t minus 7. Okay, so let's do one more. Inverse Laplace of e to the negative 2s over s times s plus 3. Okay, so I have a unit step function at 2, and my g of s is 1 over s times s plus 3. Oh boy. Okay, partial fraction decomposition gives us 1/3 times 1 over s minus 1/3 times 1 over s plus 3. So that came from a g of t equal to 1/3 times, times 1 minus 1/3 times e to the negative 3t. So that's the function I'd like to put in there, but everywhere I see a t, I have to put in a t minus 2. So all times u sub 2, all times 1/3. There is no t to plug in there. Minus 1/3 e to the negative 3t. And before I put the t, I need to put in a t minus 2 to reflect the shift. Okay, practice these in your homework a lot, going back and forth with the inverse Laplace and the regular Laplace. I want to do 2 examples of initial value problems, and they are time consuming. I'm also going to be skipping lots of steps like I did here, where I'm doing the partial fraction stuff for you, but they're still really long problems. So let's get started. So we're going to solve y double prime plus 2y prime plus 3y equals f of t. To save us a little bit of time, I need to tell you that y of 0 and y prime of 0 are 0. And f of t is given by the piecewise function 0 when t is between 0 and 3, and t when t is greater than or equal to 3. So it'd be a good idea to rewrite that differential equation in unit step function form. Y double prime plus 2y prime plus 3y equals the unit step function at 3 times t. So we're basically turning on y equals t at time 3. Okay, take the Laplace of both sides. And away we go. So remember, the Laplace of the second derivative was s squared times the Laplace of y minus s times y of 0 minus y prime of 0 plus 2 times y prime. The Laplace of that was 2s times the Laplace of y minus 2 times y of 0 plus 3 times the Laplace of y. I barely fit this in there. The Laplace of, I'm just going to write it like that for right now, u3 times t. There we go, because I don't have room to write it all. So let's see. This will really help, though. All of those y's and y primes are 0. So let's write this. S squared plus 2s plus 3 times the Laplace of y is equal to, okay, the Laplace of the unit step function at 3 times t. So that will be e to the negative 3s. The t, dang it, doesn't have the shift we're looking for. So it should be the Laplace of t, it was t minus 3 and then plus 3. So the Laplace of t minus 3. So times the Laplace of t plus 3. Okay, so let me finish this side on the right-hand side real quick. This is e to the negative 3s times the quantity. The Laplace of t is 1 over s squared. The Laplace of 3 is 3 over s. So I have 1 over s squared plus 3 over s. Okay, remember our goal is to isolate L of y. So the Laplace of y is equal to e to the negative 3s times the quantity. I want to combine these into one fraction, the 1 over s squared plus 3 over s. So I'll have 3s plus 1 divided by s squared times the s squared plus 2s plus 3 from the left-hand side. And it is annoying as heck, but it doesn't factor, the s squared plus 2s plus 3. So we'll have to use completing the square when we get there. Now, I've done all of your homework problems, and I'm here to tell you, when you do partial fraction decomposition, like we're going to have to here, the coefficients don't always turn out to be integers. So I'm going to do the PFD part for you here, but you should know that just because you get ugly fractions doesn't mean that you made a mistake. So here's what we get when we do this. 7/9 over s plus 1/3 over s squared plus negative 7/9 s minus 17/9 all over s squared plus 2s plus 3. Okay, scooch this up, keep going. Now, I'm going to do an aside here for this fraction, the negative 7/9 s minus 17/9 over s squared plus 2s plus 3, and then we'll come back to the whole thing because we're about ready. If we can get this awful fraction into something inverse Laplaceable, I don't think that's a word, but we're going to make it one. I'm happy with the e to the negative s. I know that's a unit step function, a constant over s, a constant over s squared. The first few are fine. It's this sucker. So the first thing I want to do is write that this denominator would really be, after you complete the square, s plus 1 quantity squared and then plus 2. So if you complete the square on that, you should get s plus 1 quantity squared and then plus 2. That means in the numerator, where we have the 7/9 s, we want a 7/9 s plus 1 so that the s plus 1 portion can match the s plus 1 quantity squared in the denominator. Okay, so that would be like subtracting 7/9. So let's add 7/9. And then we have negative 17/9. So what we have in red right here is technically subtracting and then adding 7/9. So we've got negative 7/9 times s plus 1 over s plus 1 squared plus 2. A pretty decent cosine. And then we have minus 10/9 times 1 over s plus 1 squared plus 2. A halfway decent sine. Now remember, sine needed the square root of this constant term, so we should have the square root of 2 up there to make it a true sine. So we need to multiply by 1 over square root 2 on the outside to make it compensate. Okay, so here we go. We shift up just a little bit. Just a little bit. So we've got the Laplace of y is equal to e to the negative 3s times the 7/9 over s plus the 1/3 over s squared, and now minus 7/9 times s plus 1 over s plus 1 squared plus 2. Nice cosine. Minus 10 over 9 root 2 times root 2 times s plus over s plus 1 squared plus 2. A pretty nice sine. Okay. Taking the inverse Laplace of both sides, we have inverse Laplace of the Laplace of y is y. E to the negative 3s. here's what I want you to remember. E to the negative 3s means you're going to do two things. You're going to put in unit step function at 3, and you're going to replace all t's with t minus 3. So e to the negative 3s means you do two things. You put in the unit step function at 3, and you replace all of your t's with t minus 3. So here's the unit step function at 3. First one isn't so bad. 7/9 over s, that's just a constant. So it just stays 7/9. 1/3 over s squared should be 1/3 t, but we're going to make it 1/3 t minus 3. Minus 7/9 times s plus 1 over s plus 1 root 2. Oh my gosh. Now here's the doozy. That is a first shifting theorem problem like we practiced in 10.5. So this has, if you remember, e to the negative t from the s plus 1. Oh, but I was told replace all of your t's with t minus 3. So that should be t minus 3. So the stuff we put in blue there, the e to the negative t, that's from the first shifting theorem, the s plus 1s. The red, the minus 3 part, is the second shifting theorem from the unit step function. Okay. So going on, this was cosine of root 2t, but everywhere I see a t, I'm supposed to replace it with a t minus 3. Okay, minus 10 over 9 root 2. So this is a sine, but this is a sine with a first shifting theorem also, the s plus 1. So this is e, I want to say e to the, oh, I want this in blue, sorry. E to the negative t, but there's a t. So I have to put a minus 3. Everywhere I see a t, I have to put with minus 3 because of the second shifting. Times sine, whoops, sine of root 2. I want to say root 2 times t, but I have to put in a t minus 3 because of the second shifting theorem. Holy cannolis. And we're done. Whoa, that is not good. There we go. That's a little bit better. Okay, let's try one more of these. Okay, so we're going to solve y double prime minus y prime plus 2y equals f of t, where let's see, y of 0 is 0, but I really want to do one where one of them is not, so y prime of 0 we'll say is 1. And f of t is equal to 0 when t is between 0 and 2, and t squared when t is bigger than or equal to 2. So writing that as a unit step function, I have y double prime minus y prime plus 2y equals the unit step function at 2 times t squared. Okay? Taking the Laplace of both sides. I've got s squared times the Laplace of y minus s times y of 0 minus y prime of 0. Then for the minus y prime, s times the Laplace of y plus y of 0 plus 2 times the Laplace of y equals, let's see, can I fit this here? I think I can. The Laplace of the unit step function at 2 is e to the negative 2s. T squared doesn't have the correct shift, so we have to do the Laplace of t plus 2 squared, which is going to be the Laplace of t squared plus 4t plus 4. Okay, let's keep going. So the thing, what cancels here? Oh, all of my y of zeros cancel. So this is 0, not that one, and this one's 0, and this is 1. So what do we have? We've got s squared minus s plus 2 times the Laplace of y minus 1 equals e to the negative 2s times the quantity. Okay, Laplace of t squared is 2 factorial over s cubed. The Laplace of 4t is 4 over s squared. And the Laplace of 4 is 4 over s. Before I keep going, a comment on notation that's really important. I know there's a lot of writing associated with this. I know that. And I know, because I am quite lazy, it's tempting to not write the Laplace of y every time. Maybe to just write an L. You must write the of y part to earn full credit, because it's akin to writing square root minus 3 square root plus 4, which might be fine for scratch paper that people don't see, but is not fine to turn in. So write the Laplace of y each time. I do not care personally whether you put parentheses or brackets, but that's that's about the only thing. Okay, gosh darn it, s squared minus s plus 2 doesn't factor. So we have two things to do. We have to add the 1 to both sides. So we've got s squared s squared minus s plus 2 times the Laplace of y equals 1 plus e to the negative 2s. And I may as well combine these into a single fraction. 4s squared plus 4s plus 2 all over s cubed. And then divide both sides by s squared minus s plus 2. Okay, scooch up so we can do that. So our Laplace of y is isolated equals 1 over, and I'm going to do completing the square on that. That is s minus 1/2 squared plus 7/4 plus e to the negative 2s times 4s squared plus 4s plus 2 over s cubed times the quantity s minus 1/2 squared plus 7/4. Okay, when you're doing the partial fraction decomposition for this ugly thing multiplied by the 4s, the e to the negative 2s, I guess, you might want to leave this as s squared minus s plus 2 times s cubed. But completing the square form is certainly nice for when we take the Laplace, inverse Laplace. So when we do partial fraction on the other side, we've got, which you will show me on a test or a quiz. So I'm going to write lots of PFD here. And here's what we're going to get. The first part stays 1 over s minus 1/2 squared plus 7/4 plus e to the negative 2s times, okay, here we go, 11/4 over s plus 5/2 over s squared plus 1 over s cubed plus negative 11/4 s plus 1/4 over s minus 1/2 squared plus 7/4. Okay, again, I'm going to take that last sucker of the cosine and sine and do an aside so I don't have to keep writing everything else. And it'll actually help me with the first one too. So the first one, I have a constant in the numerator. So I know this is a sine, and I know I want the square root of whatever the b squared is over here. So I want I'll do this in red, a square root of 7 over 2 in the numerator. So I need to multiply by 2 over root 7 on the outside. And I'll do the same thing in here when I get to that point. So let's see. This will become negative 11 fourths s. I want minus 1/2. So I'm going to need to, let's see, that was actually adding on an 11/8. So we need to subtract 11/8 to make up for that. And then we had the 1/4 pre-existing over s minus 1/2 squared plus 7/4. Cool. Okay, so that gives us negative 11/4 times s minus 1/2 over s minus 1/2 squared plus 7/4. What's that? Negative 9/8. 9/8. S minus 1/2 squared plus 7/4. But just like the very first fraction we did up here, I want there to be, because it's a sine, a root 7 over 2. So I'll multiply by 2 over root 7 on the outside. All right. Almost done. Almost done. Okay. So let's take the Laplace of, let's write the Laplace of y one more time. So we've got 2 over root 7 times root 7 over 2 over s minus 1/2 squared plus 7/4 plus e to the negative 2s times the quantity 11/4 over s plus 5/2 over s squared plus 1 over s cubed minus 11/4 times s minus 1/2 over s minus 1/2 squared plus 7/4 minus, what's that going to be? 9 over 4 root 7 times root 7 over 2 s minus 1/2 squared plus 7/4. Cool. Okay, take the inverse Laplace of both sides. And away we go. So y equals 2 over root 7. Okay, so looking at this, we have a first shifting theorem in our sign because we have s minus 1/2 squared. So that will be multiplied by e to the 1/2 t times sine of root 7 over 2t. Okay, so we had a first shifting theorem in there with the e to the 1/2 t, but not a second shifting theorem. That comes in the second part. So the second shifting theorem is the harder one to keep track of. The second shifting theorem right here means with the e to the negative 2s, we need to put the u2, well that's fine, we won't forget that, and then replace all of our t's with t minus 2, all of them. So that will be, oh, I need more room. There we go. That will be u sub 2 times the quantity 11/4. Because that's 11/4 over s, inverse Laplace is just 11/4. But the 5/2 s squared came from a t, so this will be 5/2 t minus 2. The 1 over s cubed came from a t squared, but it should have been a 2 over t squared. It should have been a 2 factorial, so there should be a 2 factorial in the bottom. So we have 1 over 2 factorial, or 1 over 2, times t minus 2 squared. Okay, minus 11/4. Oh boy, now here's the brutal ones. It's in a second shifting theorem portion, and it also has a first shifting theorem. So I want to put E for the first shifting theorem to the 1/2 t, but since I'm inside the second shifting theorem, I have to put t minus 2 times, what color do I have? Times cosine of root 7 over 2, and I want to put a t, but I need t minus 2. Okay. Don't have room for my sign, so I think I can zoom out. Yeah. Hold please while I adjust. Okay. And then minus 9 over 4 root 7. So this sign has a first shifting theorem, and it's inside a second shifting theorem. So this will be, for the first shifting theorem, e to the 1/2 t, but I need to put a t minus 2, sine of root 7 over 2. I want to put a t, but I'm in the second shifting theorem, so t minus 2. Sorry that I sometimes did the blue and sometimes I didn't. So here's my 2. That accommodates the t minus 2 here, t minus 2 here, t minus 2, t minus 2, t minus 2. Done. One thing to point out, if you were in class, I would ask you, why didn't I put a t minus 2 out here? Because it wasn't part of the second shifting theorem. Okay. Done.